This is the last talk of the AM session, and it's by Eero Saksman from Helsinki, who's going to talk about Riesz projections, BMO, and Dirichlet series.
Thanks, Bill. It's a great pleasure to me to be around in this program, and thanks for the invitation. And it's nice to. I saw when I went through some of the participants in Zoom that there are many friends and colleagues. So nice to meet you all via Zoom. And by the way, are there many people around really in Toronto, or is there no actual program going on, or is it all in Zoom? Or
it is all in Zoom. I'm in Toronto, but maybe and Ignacio is also in Toronto, but that's all.
Okay. So I will tell you about something about a joint paper with Sergei Konyakin, Erve Kefelek, and Christian Seip, and it's supposed to appear fairly soon. But at least it's been preprint already for some time. And I don't know exactly how much I can tell you about BMO. So somehow I put this BMO here. I can maybe make some remarks on BMO related to these things, but maybe to try to have some connection. It's more like this analytic function spaces. And so let me start. Some of you may know, but not everybody for sure, about this function spaces of Dirichlet series. And let me start by first explaining what is H2 space of Dirichlet series. So what is a Dirichlet series? Dirichlet series is something that you can write as a sum like this, and this is so-called standard or ordinary Dirichlet series. So you have some n to minus s. S is a complex parameter, and usually it is customary here to say that to use the variable s instead of z. So s is sigma plus it, so sigma is the real part of S and t is the imaginary part of S. And some years ago, actually more than 20 years ago, it was Christian Lindquist. So Herman Lewis and Seip, they defined a Hilbert space of Dirichlet series. It kind of turned out that it had started a systematic study of these spaces, and the norm in this space is defined in a very simple way. So it is just the square sum of the coefficients. It's of course is the standard Hardy H2 space in the disk. And if you use Cauchy-Schwarz, you will see that at least to the right from sigma equals 1/2. And that's in general the best you can hope for. These spaces and their properties have been studied in quite a few papers ever since, and it turned out that some results that had been done in the past actually can be interpreted as results for these spaces or operators on these spaces. And not just to, I will not speak much of these spaces, but they are somehow the part of the underlying motivation for all that will be done in my talk. And By the way, I hope that you interrupt me if I'm unclear or if you want to ask anything. You can also define in this space, and it's surprising that the H infinity space actually consists of Dirichlet series that lie in H2, but they also extend analytically up to the imaginary axis. So here is the analytic domain for H2, but H infinity goes up to the imaginary axis. So you assume that the function continues analytically up to the axis, the whole right half plane, and then you assume that it's bounded there. So the standard bounded function there. It seems that my connection is not so good. I see what happens in what I write here maybe in 20 seconds later than, so in my computer I see it later than in my iPad. So, but I hope that you can still hear me somehow, at least.
We can still hear you.
Okay, good. So you can also define HP spaces. These were done by Bayard, and they also have been studied by many people. And if F is a polynomial, so by Dirichlet polynomial, we just mean that this sum here is finite. There are only finitely many non-zero ANs there. And then you can also define HP norm, and you do it on the imaginary axis. It turns out that this average of the standard LP norm exists when capital T goes to infinity, and it defines norm. Maybe I should have here to power P. And now these spaces are closely related to Hardy spaces in infinite dimensions. And the connection here is that is via so-called Bohr isomorphism. So what the Bohr isomorphism does, it associates any, for example, any HP function on the infinite dimensional torus Dirichlet series. And it goes as follows. So first of all, this T infinity, so it's just the torus times torus, one-dimensional torus, so on, times itself infinite many times. And the measure there is just a normalized Lebesgue measure. And the HP spaces, they actually, okay, if you are on the boundary, so on this torus, so all the points there on the boundary, you can write as sequences where Zn is 1 for each n. And as a functions of these variables, these spaces are spanned by the analytic polynomials. So typical element there is some constant times Z1 to power alpha 1, so on Ck to power alpha k, and here alpha 1 alpha k, they are positive integers. And if you would like to span the whole LP space onto the torus, then you would allow here also negative powers. But for the analytic functions, you have all the indices here positive. And of course, HP. What is then HP space? This script HP space. This HP on the infinite dimensional torus is just the span of these kind of elements. So this is the span of these guys, and you take the span in LP of the measure space. So just like the usual analytic functions are spanned by z to the k for positive k on the one-dimensional toes. Okay, and the Bohr isomorphism says that this kind of element z1 to alpha 1, so on zl to alpha l is mapped to the one basis element of the Dirichlet series. So it goes to n minus s, where n is the prime p1 to power alpha 1, so on pl to power alpha l. So this is the Bohr isomorphism. And it turns out that it is a linear isometric isomorphism between these spaces. So this isomorphism here is linear, it's isometric, and it's even algebra isomorphisms. You can even multiply functions and they go to the product of the space. Okay. So in that sense, the study of these spaces is about the same. You have two different point of views to the same spaces. Now in this talk, so what do we want to do? So we want to answer the question of Marzo, Jordi Marzo and Christian Seip from about 10 years ago or 11 years ago. And I hope that I can be pretty elementary here. The proof is not very long, and we don't need any advanced techniques. So I think that I can try to present the proof for you. So that's actually what I try to do here. And then if there's time, I can make some remarks on what we also proved on BMO space with that series. But in some sense, our work on the BMO spaces was not so successful that we got some results, and hopefully some of them are non-trivial, but we are kind of missing definite results in a certain sense, if one wants to be critical to what we did. So what is this question of Marzo and Seip? Now I'm using the same, I want to recall you the notation. So T infinity with the hard measure or with the product of the normal measures. And you can look at this. You don't need not only to look at the infinite torus in any dimension. So we also will look at the HP on Tn. And whenever I have a point Tn, I will denote it by, as we already did before. So here Z1, so on Zn, or unimodular. Okay. So what is the question? So let me motivate it by going through with some detail a one-dimensional case. So let me denote by P plus N the n-dimensional Riesz projection. So it is just a standard type projection, orthogonal projection on L2, from L2 to the analytic functions. Now you can write any function in L2 of Tn. you can write it as z equals k n times z to the n, u1 to the n1, and so on. Let's say k1, z n to the kn, and now k1 and kn, they belong to z. So it is an n-fold sum over all integers, and the negative powers are well defined because you are on the boundary. Z ones are unimodular. So this is just a standard n-dimensional Fourier series on the n-dimensional torus, nothing more. And when the Riesz projection then just kills all the elements in this sum which have at least one index here negative. So in other words, what you are looking, let's say in 2 dimensions, if you write the indices here, you're projecting on the positive, or let's say non-negative index pairs. So to the positive octant. Okay. Now what we are asking is that could this projection have a contour behavior? It sounds a little bit weird question. And it's clear that P plus M, it maps L2 into L2 contractively. It's a funny thing. I've been writing already a long time ago, but you don't see what I'm writing. I'm sorry for the connection. Now you see it. It came here. Okay. I had a lecture today. I'm at countryside. Usually here the connection is better than in Helsinki, but today. So in any case, it's clear if I map into H2, then this is a contraction. Because of course P plus is contraction of L2, and the L2 norm is less than L infinity norm. But could you have some other exponents than 2, where it could be contraction? And the slightly surprising answer is yes, there are. So let's look first at the 1 dimension. So it's just been out in 1 dimension. Now I'm already in the next page, but I guess you changed. Okay. In 1 dimension, I did Riesz projection by P plus, and P minus is then the remaining projection, or so identity minus P plus. Proved 10 years ago was that actually contractive from L infinity to LP exactly when P is less than is quite nice. It's kind of fun. So let us first some fun with the proof. What do you prove? So take any element in L infinity, and then notice that the square of the Riesz projection. To the square of p minus f squared. Powers of z, and this contains powers of z. Now I cannot even point, so it comes so late. I cannot do anything. So what in the next line is that I've started to compute the fourth norm of p plus f. And first I write it as the L2 norm squared of the norm of the square. And then I can take off this p minus f squared because they are orthogonal. Norm is just increasing. Okay. Squares, so you get f as one factor, and then you have the diff of this of p plus and p minus. Maybe the only way to, because this pointing doesn't show, so maybe I try to only move this thing, not to point. What can I do? So here you have a f times this thing here. You can take off. Bill, can you hear me still?
We can hear you. You're breaking up a bit from time to time, but we can still hear you.
Yeah, thanks. Yes. Okay, so I can factorize this f out of here, so taking the subnorm of f, and what remains is p plus minus p minus f L2 norm, but of course it doesn't matter if I multiply the Fourier coefficients by, if I change the signs, so equally well I can compute the L2 norm of f, which is certainly less than L infinity norm of f. So after all, what we get, I get okay, so it's a cute observation. And to show that this is optimal, you can consider the function f
Okay, hopefully Eero will come back in. Oh, Eero, we seem to lost your slides.
Can you hear me now?
I can hear you, but we can't see any of your slides.
Yes, yes. Let me try. They are repairing some link close to here because it used to be an excellent connection here.
Oh,
And I can go else, go to any other place. Okay, so can you don't see anything yet?
well, we just see your iPad, not any specific file.
Yes. It's also a bit funny that it goes like that.
Here we go.
Okay. Okay, let's go as long as we can. To show optimality, you apply this kind of simple function. So fz equals 1 minus epsilon z over 1 minus epsilon z bar. Now the good thing about this p plus f, p plus f is just the first degree polynomial, what it is. So, and that delta equals epsilon over 1 minus epsilon squared. When you use plus the power p, you just put this representation there, and so you use binomial series, and after some computation, you get the main terms. Binomial series, and all terms contribute. Now we see what is the Fourier series of p plus f to power p, and of course the integral of the constant terms you obtain by multiplying 1 by 1, the z by z bar, and so on. So actually, it's very easy to compute, and at the end, after the dust settles, what you get is that you have a 1 plus p over 4 times p plus lower order terms. You see that if p is larger than 4, you are doomed by letting epsilon go to 0, because the function has infinite normal 1. You would like to get something less than equal to 1. Okay, so it's a very cute observation. And actually, there was a paper before by Fikiel, Pelczynski, and Ivan Riesz, who considered similar questions for certain projections. And they also observed for some other projections that the critical exponent is 4. So they actually looked at the projection on the span of 1 and z, for example. And now what we want to do, we want to define n, where n is now the dimension of the torus. So we want critical exponent Pn by saying that Pn is the supremum of p larger than or equal to 2, such that Riesz projection is contracted from L infinity to LP. And if n is larger than 2, things are less obvious. For example, we can even ask that, is it clear that Pn is larger than, what about P infinity? So then n goes to infinity, or if you look at directly the infinite dimensional Riesz projection, you still have contractility. And March and Sape, they showed that actually Pn is strictly between 2 and 4, for n larger than or equal to 2. And the main question that remain, for example, you can ask for the precise value of Pn or how it behaves asymptotically, with right asymptotics. But the real question for many case, so is P infinity equal to 2 or not? From L, you are always contracted to L2, but in infinite dimensions, can you be contracted to a higher exponent than 2? And this turned out to be not so trivial. The paper by wrong page. Oh, now I should not leave the page. Sorry, I will not leave. The original paper from 2011 gave some estimates. It showed that P infinity is less than 3.67, and Ole Breivik then was able to improve this to 3.3 a couple of years ago. And but now after our paper, we know the answer, which is kind of the expected answer, that in infinite dimensions you cannot do better. But it's P infinity is although the connection is not working well. Some of the idea of the proof let me recall the Dirichlet kernel in one dimension. So here you see Dn is the Dirichlet kernel in one dimension. We certainly know how its knobs behave. The L1 norm of the Dirichlet kernel blows up. It's the fact that Fourier series don't converge for every convergence function, and the LQ norm is easy to compute. Actually, the highest peak around origin dominates for larger than 1. So you get easily that it's n to the power 1 minus 1 over q. In higher dimensions, you can make different kind of Fourier summing of Fourier series, and one way to sum is to use sum over all frequencies that lie in a cube, and that corresponds to the kernels, which are denoted here by subindex dn small n and c, and here the n is now the radius. You could maybe use capital R, but for some reason I used capital N. Used to think it's the radius. It's actually half the diameter of the half the side length of the cube. And of course, for the cubical Fourier summation, it's now very easy to compute how this L1 norms and LQ norms behave. And this L1 norm is often called the Lebesgue constant for a summation method. And so the Lebesgue constant in one dimension is about log n, and in n dimensions it's n. But then you can ask for other kind of summations. And here we are asking, how does the Lebesgue constant behave for spherical summation? So what if you have a sum over balls? You look at all the frequencies that are less than capital N. So this is the spherical summation of free series. And there's a quite famous theorem due to Papenko and Ilin around year 70. I don't know the exact year, but that this actually blows up polynomially in n, depending on the dimension. So the Lebesgue constant, the L1 norm of this guy behaves in much worse way than in one dimension, or even in n dimension. Because in n dimension, we had it. It's just the power of a logarithm, and this is a factor. This phenomenon we will use in the proof. So let's go to the proof. And what is the idea of the proof? So there are several things. We want to use the spherical Fourier summation Lebesgue constant, but the trouble is that we cannot do exactly the ball. But what we can do, as you will see, we can handle convex polytope. It's just a convex body which is bounded by, let's say, which is an intersection of half planes, half spaces, intersection of half spaces. And with rational data means just that the coefficients of the linear equation defining this half space are rational numbers, or equally you can assume that they are integers. So what we will do, we will apply the spherical Fourier multiplier, but we have to approximate it with the rational polytope. And then we have to relate the Fourier multiplier to Riesz projection. And as I already said, we want to use the Lebesgue constant. We actually want to use the discrepancy between the Lebesgue constant of a cube and a ball in higher dimensions. And then there's a simple duality argument. But, that's basic things are already here. And the main question here is that how do we relate the Fourier multiplier chi a to the Riesz projection? And now that is done in the following way, that you increase the dimension. So here, if you look at the Fourier multiplier of the polytope lies in some dimension. Then what you do is you take we will relate it to the Riesz projection in much higher dimension, and that's the way to go. And it doesn't matter that we are taking the higher dimension, because our aim is to prove that something is not uniformly bounded, or is not uniformly below 1. It's not contractive, so it doesn't matter. We can take all the possible dimensions we want here. Okay, let's take a toy example and consider in dimension 1 the following very simple Fourier multiplier. which kind of corresponds to one-dimensional polytope. So how do you cook up this by using the Riesz transform? If you try to do it in one dimension alone, what you would do is that you would maybe make some shifts and action of the Riesz transform twice. With a couple of actions of the Riesz transform, you could kind of try to cut it. But then you already have to apply easily many times. But what we do here is that we add the number of the variables. So instead, you replace this trigonometric polynomial by this polynomial where you have increased the number of variables and put here z1, z2 to positive power, z3 to negative power. And then you put suitable numbers in front. And this I call f tilde. So it is kind of lift of f to 3 dimensions. And then this doesn't change the LQ norms at all. Because what you can do, you can first compute the norm with respect to Z2 in Fubini. But then these are just constants which don't play, these are just for fixed values, this is just a constant. It doesn't change the LQ norm. And these are just unimodular things in front, so they don't change the norm. So norms are same. In the same way, but then by the definition, just from the definition of the projection, you see that actually this 3-dimensional Riesz transform acting on this guy is exactly the tilde of thing that when I apply by the Riesz transform, 3-dimensional Riesz transform, it kills all between A and B by definition of the Riesz transform. Okay, so let's let's go on. You can play the same game in higher dimensions. You just use more auxiliary variables. M is now the number of auxiliary variables. You define these exponents in suitable way. And let's not, it's just the same idea. And what happens is that I can represent the Fourier multiplier corresponding to this kind of convex polytope by with rational vertices or rational data, maybe better, by the same idea. Especially, it follows that if P is, if there is a transform, would be contractive for all n, for all capital N with some fixed P. So P is of course fixed. Then all those Fourier multipliers that we constructed above would be contractive. Okay. Now what we need to do, if I use duality, so we are looking at something from L infinite to LP. So in other words, now we are looking at something from LQ to L1, where Q is less than 2. So I need to find for any given Q some F in such a way that this let's say spherical convex, this kind of Fourier multiplier corresponding to a bounded convex set, characteristic function of the bounded convex set, increases the L1 norm makes it larger than LQ norm. That would be enough. And what you do is that you actually take your function f to be the summation corresponding to the kernel, the partial sum kernel corresponding to a cube, and then you hit it by a multiplier, which is just a ball inside the cube. And when you do the algebra by using the data we have, we know what is norm of f. So f is now the one-dimensional, is now the n-dimensional n-dimensional kernel corresponding to cubical summation. So that norm we already stated before, it's here, it's the LQ norm. On the other hand, by the Babenko and Ilin, or maybe I should say Ilin-Babenko, Ilin was maybe first with this result. So Ilin-Babenko result on the Lebesgue constants, you actually have this estimate. And if Q is small, you have to choose n very large to get the contradiction here, but you can do it always. You just need to choose this guy to be larger than this, and that you can do if Q is less than 2. And you let n, capital N to go to infinite. So you get a discrepancy between these estimates. And that's basically the proof. So what is why were we interested on this with respect to the, what comes to the analytic function spaces, to the spaces of Dirichlet series? And the reason is that it has a couple of implications. So it implies, for example, that the dual of the script H1 space, so this is now the Hardy H1 space of Dirichlet series, its dual is not included to any HP space if P is larger than 2. Which is in a very sharp contrast to one-dimensional case. Because in one-dimensional case, this is BMO. BMO is certainly included to all LP spaces where P is less than infinite. So this again testifies for the quite weird nature of these spaces of Dirichlet series. And I was prepared to tell you a little bit about random Dirichlet series BMOA, or then second topic, I could have told you alternately a little bit when this series of Dirichlet series lies in a BMO space in the right half space. But I thought I would have time for one of these topics, but if you're interested, you can take a look at our papers. So I think that I will simply stop here and thank for your attention. Thank you.
Oh, thank you. If anybody has any comments, just shout them out or put them in the chat.
Excuse me? Yes?
Yeah.
Yep.
So this says something about the limit P infinity, right? And is there a way to get from that any estimate of how fast Pn would decrease to 2? Or, it's probably hard with all the steps involved. But...
Yeah, that's an excellent question. There are estimates already in the paper by Jordi Macha and Christian Seip originally. they give some lower bound how quickly Pn can tend to 2, and but as far as I know, this proof what we have here, nobody has tried to check whether it really gives any real interesting bounds. I guess you can get some extremely bad bounds for the speed how you approach 2. Ole Breivik has a guess, as far as I remember, what is the correct rate, and but to be honest, I've forgotten the rate. I thought it was polynomial rate, so it's 2 plus some into some negative power, but I might be wrong here because this I don't remember now what he told me exactly. But it's a very interesting question that how Pn goes to here.
Okay, thanks.
Other comments or questions? Keeping an eye on things.
Something in the chat, but
There's one thing in the chat. I think Javad.
yes,
wants to-
about references. Sorry, I don't have a reference page for references, but if you go to arXiv and you look at there's a paper by Hervé Kefelec, Sergei Konyak, and Christian Seip, and myself. So there you have the references and actually the whole story. Sorry for this.
Okay, further comments or questions? If not, let's thank Eero again. And it looks like it's turning night in Helsinki. So
Yes, I'm surprised how quickly it goes. Yes.